All right, we're kind of in the home stretch, which is good. We'll easily finish chapter 8 today, or unit 8. We only have like 5 slides or something like that left. We only have 2 reactions, and they're quick, and they're similar to ones you've seen before, and there's no mechanism to learn. So what we're going to do after that is unit 9. Unit 9 is also quick. Unit 9 has, I think, 2 reactions you got to know, where like 8 has like 12 or something like that. So it's another short one, but it's going to be nice. It's going to be completing a few concepts. And what I'd like to do is save time at the end of the course to go through like a good amount of practice of old exams. You know, the term is running later this semester than it, I think, ever has. And so, you know, I don't want to run right up to the end with new material. So in chapter 8, all the reactions we've looked at so far have been reactions that have been addition reactions to alkenes. I guess we did some alkynes at the beginning with hydrogenation, but we did addition of hydrogen to alkenes, we did addition of HX, we did addition of water 3 different ways. We did addition of Br2 and water. We did dihydroxylation, and we did oxidative cleavage using 2 different mechanisms. 2 different reagents. We used the osmium tetroxide, and we used the KMNO4 cold. Hot. Cold does the dihydroxylation. The last 2 reactions in this unit that we're going to do are reactions of alkynes. They are analogous to reactions that we've already seen for alkenes, so there's not really a whole lot that's super new here. The first one is halogenation of alkynes. Basically, if you start with an alkyne, like you see here, triple bond, and we treat it under the same conditions that we would treat an alkene, Br2 in a non-polar solvent. CCl4, I talked about in a previous class. CCl4 is carbon tetrachloride. That's a solvent that I said has sort of gone out of favor because it will destroy the ozone layer. So we don't really use CCl4 really anymore, but any other nonpolar solvent here is fine. Hexane, whatever. What happens is if you have one equivalent, it'll add Br2 across the triple bond, reducing it from 3 bonds to 2 bonds. And what that does is you make a dibromo compound that's trans. Now you still have a double bond, you still have an alkene. So if you use 2 equivalents of Br2, you can add it twice, and you could end up with this tetrabromo compound. Works with chlorine too. That's kind of it. We're not going to do the mechanism. The only real thing here is the first one goes on trans. It was anti-addition, just like it is with alkenes. Nothing really too out of the ordinary and unusual here. We don't have a variation where we use Br2 in water. I don't know what happens in that situation. Actually, I do know what happens. It's not. Actually, I don't know what happens. The reason we're not doing a mechanism for this one is the mechanism is not as well understood, and the mechanism is it's term molecular, the rate determining step. That's really rare. It means 3 molecules come together in the rate determining step. That's something we know about it, but anyway, it's not something I'm going to ask you to draw or ask you questions about. These are just more examples. Your triple bond, regardless of what else is on the molecule, think about adding the Br2 trans like this. Cool. Next reaction, addition of HBr. This is, again, just like addition of HBr to an alkene. This also does not go through the same mechanism. It doesn't go through a carbocation. This one also is term molecular, the rate determining step. 3 molecules come together in the rate determining step. HBr will add once. It'll give you the same product, though, that you'd expect as if this was an alkene. It gives you Markovnikov addition of HBr, 1 unit, and if you add a second equivalent of HBr, it'll add a second unit to make a dibromo compound. What kind of dibromide would you call a compound like that? Not a vicinal dibromide, is it? Vicinal means they're on adjacent carbons. Geminal dibromide, very good. Yeah, this is a geminal dibromide because both bromines are on the same carbon. And this little bit at the bottom here, I mean, this is maybe, if you're interested, I don't think this is going to be, you're going to be tested on this. But HBr sometimes is a pain to use as a reagent. So sometimes what we do instead is we make the reagent that we want as part of the reaction mix. So what you can do is take this compound, which is called acetyl bromide, which has the structure that looks like this. And if that's reacted with alumina, which is a white powdery material, it's an aluminum oxide-based material, it can turn into HBr, and then you're making HBr in small amounts as needed in the reaction. There's lots of examples of reactions like this where we may draw a reagent, but whatever the reagent is might be either unsafe to ship or to handle or whatever. It might be really toxic. It might not store well. So sometimes what we do is we mix some things together to make that reagent in solution, and it's that reagent that's actually doing the work. An example of this, and this is part of the unit that we cut, or part of the one reaction in this unit that we cut, which was cyclopropane synthesis. There's a reagent you can get called diazomethane, which is CH2N2, which has a Lewis structure that looks like this, CHHNN. No. It's CNHHN. I think it's like plus minus, something like that. Anyway, that thing is like super, super toxic and is also explosive. So you can't buy a bottle of this and have it shipped to your address because it could blow up in the mail. So you can actually buy kits. It's also really toxic. Like if this gets in your skin, it'll, what it does is it'll add carbons to any nucleophile that it can find, such as, proteins and things like that. So you don't want that to happen. So you buy this kit, and the kit allows you to mix all these things together, and then you put your other reactants in, and then it'll make your product without ever having to have that single substance that's bad for you. But other than that, this reaction is straightforward. You add HBr, H goes on one side, Br on the other. You can do this up to 2 times because there's 2 pi bonds, and yeah, you get a geminal dibromide as a product. Geminal dibromides, by the way, you can, if you heat these things with water, you can actually convert that to a ketone. It's a way to make ketones, which is not something we're dealing with yet, but it's something that you can see. Maybe in organic too, we would do something like that. I guess we had another reaction, oxidative cleavage of alkynes. We did oxidative cleavage already using 2 different sets of conditions. One was KMNO4 under basic conditions. The other was ozonolysis. The only difference really with alkynes, it's a little simpler. What happens with alkynes, regardless of which of these you use, is when you cut that bond in 2, both halves become carboxylic acids. So you can see here using ozone, you get a carboxylic acid on both sides, and using KMNO4, and I think this one doesn't even require heat. This one is a little bit easier to oxidize than an alkene. But you get, again, 2 carboxylic acids on either side. So if you have a reaction like this, just think about cutting it, and then the left side becomes a carboxylic acid, and the right side becomes a carboxylic acid. Just make sure when you do this, you count your carbons and make sure you haven't lost any, because this is the big mistake people make with oxidative cleavage. They add a carbon or lose a carbon. Usually they can remember what the ends should look like, but it's making sure you haven't lost any carbons. 3, 4, 5, 5. So this becomes 1, 2, 3, 4, 5, 5. Cool. So that's it. That's the unit. We didn't do one of these. We didn't do 8 cyclopropane synthesis. But this is a good summary where we're at. We did hydrogenation, synaddition. We did not do a mechanism for that. I mean, I showed you the mechanism, you know, where it kind of lands on the surface of the metal and so on. But you don't have to draw a mechanism for that. We did addition of HX, like HBr, HCl. That is not syn and it's not anti. Gives you a mix. And yes, you have to draw the mechanism for that. And addition of water, which was 50% water, 50% sulfuric acid. These two are the same mechanisms, both ADE2. Protonate first, make a carbocation, nucleophile comes in. So yeah, both of them are Markovnikov, both of them are not syn and not anti. Oxymercuration, demercuration was sort of like reaction 3, except no rearrangements. No mechanism you need to know for that. Hydroboration oxidation was syn and anti-Markovnikov. No mechanism you need to draw for that. Addition of X2 or X2 in water, yes, you need to draw those two mechanisms. Same mechanism in both cases, essentially. And those are both anti. And then we did a bunch of sort of like, I'd say quick ones towards the end. Oxidation to vicinal diols using cold KMNO4 or osmium tetroxide. We did oxidative cleavage using, again, hot KMNO4 or ozone. We did addition of, then just the ones we did today, addition of X2, addition of HX or oxidative cleavage, all of which are analogous to reactions we've already covered or alkenes. How do you feel about chapter 8? Not good? If you guys can get chapter 6 and 7 in your heads, this one's straightforward. There's a lot of them, right? That's the overwhelming part of this chapter, is there's a lot of different ones. But if I took the reactions from 6 and 7 and lined them up, it would be long too. Right? I said, you know, reaction with a bulky alkoxide with a primary, reaction with a bulky alkoxide with a tertiary. You know, there's a whole bunch of different variations that could create a long list like this. You have to be able to recognize. But the nice thing about these reactions is typically they only go in one direction. They kind of always do the same thing. They're more reliable, and none of these have competing reactions you have to worry about on the side. That was a major concern in chapter 6 and 7, right? Or it's like, well, we can make 3 different alkene products. Which one's major? Or it can kind of do SN2 or E2, depending on the, you know, this sort of thing. This is more just like, this is the reaction. Every alkene does it. This is the product. It's almost like, remember how it looks for the alkene part, and the rest of the molecules are relevant. With the caveat of these two reactions, the two that have carbocations, they can rearrange, just like carbocations have been rearranging all along. That's the only additional piece. We have, you know, what I want to do towards the end is pick up questions that use these reactions, and I have a few examples here. Although I could do this maybe, but maybe not the rest of them, only because coming after use reactions we haven't yet. They're in chapter 9, unit 9. But this is an example of how you can chain together some reactions that you know from this unit and from the previous unit and future units once we get there, and really figure out, you know, these maps, you know, how we can go multiple steps, how we can go in multiple directions with a given reagent. So this one says, complete the following scheme by drawing the structures of products A to F below. Reagents next to the arrows are used to carry out the step in that direction. Between the boxes for A and B, conditions for the forward are the top ones. For the bottom one, it's this. So looking at that first one, what would happen if you reacted that with HBr? HBr would protonate, make a tertiary carbocation, nucleophile would attack, and you would get a molecule that looks like this. Carbon addition goes to the more substituted side. And what would happen to that molecule then if you treated it with sodium small alkoxide, and you're thinking to yourself, I forget this already. We wrote the midterm last week, but it's gone. Get it back in there. You can't let go of that until after the exam. That's what I think, something I think about, you know, courses like this and other courses. It's like, yeah, you know what, like you're learning all this stuff, you know it super well when you go write the midterm, and then maybe 3 months later you don't remember any of it anymore. But if you ever had to learn it again, you'd learn it really quickly. And some of it you learn, some of it you always remember. I know that because when I came here to teach this course, I completed a PhD in organic chemistry. I did 4 years at a bench doing reactions and going to conferences and all this stuff. I forgot, I didn't know 90% of what I was teaching because I never used that part of what we were doing. I knew a lot about other areas that aren't covered in this course. So I learned it since, but it like, you know, I go through the book and it was just instant that I could learn it again because I've seen enough similar to it that's very quick. Yes?
Don't mind me asking, what did you do your research on?
I did my research on, it's a reaction called excited state intramolecular proton transfer. So it's photochemistry. It's looking at how the reactivity of a molecule changes when you expose it to light. And it's funny because all these rules that I'm teaching you, general rules about how organic molecules will behave towards a nucleophile or acid bases or all these sorts of things, they all change when you put something in an excited state in certain ways and in predictable ways. And so trying to understand how to develop reactions like the reactions we're learning here that are excited state reactions that give you products that you want and the products that are predictable, and, you know, ultimately trying to use those reactions for some purpose. So the specific reaction I was working on, I can show you very quickly in one reaction. If you take a phenol like this one, this has a pKa of around 10. So not a very strong acid. It's about 100,000 times weaker than acetic acid, but it's about 1,000,000 times stronger than ethanol. So it's somewhere in between. If you excite this thing, which we call pKa star, it's around like 1. So it becomes like really strong acid only for like 10 nanoseconds once it's absorbed light. And this will do a reaction to make this thing where basically the proton has transferred this carbon to make CH2 there. So it's like, that's a benzene ring that it attached to, which we'll learn in organic too are like super unreactive. It's really difficult to do a reaction on a benzene ring like that. But this will happen, this would never happen under ordinary thermal conditions, but it can happen if you shine light on it. So I looked at this particular reaction and then a whole bunch of variations, trying to figure out what conditions make it work better, what other things you can put on the rings that either makes the reaction go better or worse. And yeah, it worked out pretty well. Okay, let's finish this one off. Going forwards, we have what I would say are E2 conditions. E2, small oxide will give you the Zaitsev product, which is that one. Going backwards and reverse, you'll get A back from B by reacting with HBr. So now we go the bottom way. ClOH. That was one of the new reactions we learned in this chapter. Now it's looking for two products. That's because we have a chiral center here, which could be R or S. Next, we have KMnO4 and NaOH and heat. So with heat, that's the oxidative cleavage. And what that would do is cut the bond there, which would give you a ketone on one side. The other one with KMnO4, that oxidizes it all the way up to CO2, if it's a CH2. That's what we have here. So this is an example of using multiple of these reactions. There's another type, looks like this. You can see over here is the start. And here we've drawn a whole bunch of different products, and you have to give the conditions that get you from one step to the next step to the next step to the next step. And it says fill 10 of the 12. That's what this is asking for. But this first one, just HCl would do it. Then the next one, we want to do an elimination to give you the Markovnikov product. That would be like a small alkoxide probably. And then from this, you're doing bromination, Br2, and hexanes maybe. Then we got to do a double elimination. So this was NaNH2. This is the very tail end of chapter 7. And NH3 is our solvent here. We need two equivalents. Then we're doing addition of hydrogen to give you a cis alkene, which is hydrogenation, and then our palladium. So again, these are all reactions you're probably not super yet familiar with, but some of them you should be familiar with, like this one. But yeah, you'll get there. This one is just hydrogenation with like platinum or something like that. This next one is unit 9. Then we have another elimination. Then we're doing bromination. This is also a unit 9 reaction. This is the one we cut. So I'm going to kind of skip that bottom left corner because we're not 100% there yet. But these are the kinds of like maps that we create and showing how you can start from one molecule and make really anything else that's on this page, and thousands of other things more. There's a worry, I guess, in synthetic chemists, organic chemists, that a lot of the synthetic compounds that we use, that we buy to do reactions, to make medicines and so on, are derived from oil. And we take oil out of the ground and we burn it, but that's only one of the uses we have for oil. Like vanilla extract, for example, comes from oil, comes from benzene, which comes from oil. So if the oil industry shuts down, where people completely shift away from fossil fuels for energy, we'll still need the products of oil for these other purposes, also for making plastics, although we should shift away from that too, maybe. But there's a belief that if you can start with ethanol, that you can make any other organic molecule using combinations of steps of reactions like this, that you could take ethanol. We already know a couple of reactions of ethanol. You could react ethanol with HBr and make ethyl bromide. You could then take ethyl bromide and you could react it with cyanide and make the chain longer. Like, you could always plug together all the reactions that we know. So really, as long as we have a source of ethanol, and ethanol you can get from corn, then we're good as far as doesn't mean, though, that we're out of luck if oil dries up. This is another kind of reaction, and I'm going to focus more on this when we get there. But these are ones where you start with a certain molecule, and you have an ending molecule, and there's a couple of steps, 2 or more steps, you need to put in sequence to get from the first one to the last one. These are my favorite questions of all, because these are probably the most creative. Requires you to understand the reactions at a different level than just being able to fill in a box with the products that we want. So for example, this one, you're making an alkyne. The more you do them, the easier they get, of course, but this alkyne, there's only one reaction we looked at that made alkynes, so it makes this question a little bit easier. And that reaction was if you have a vicinal dibromide with NaNH2, 2 equiv, and then from that to that is just Br2. So this is a sequence of 2 reactions to get you there. I don't want to spend more time on that only because some of these involve reactions that we haven't covered yet in Unit 9. And this would be, I think, a good time to jump into Unit 9. How do you feel about that? Awesome? Yeah. Now these aren't too bad. Honestly, the toughest stuff is 6 and 7. Not lying at all there. Toughest stuff in all of undergrad for organic chem is 6 and 7. Why do we start with it? I don't know. The reason we start with it is because there's so many fundamental ideas in those 2 chapters that you see come back again and again and again. In fact, I think there's like 4 things you got to know in organic chemistry, and every reaction, the way it goes, is a result of like knowing those like 4 things. One of them is like resonance stabilizes things, makes them more reactive or less reactive if it's resonance stabilized. One is electronegativity and where the electron density is. A lot of electron density in one place makes something a good nucleophile. A lot of positive electron density in one place makes it a good electrophile. Size, steric bulk, reactions are slow if there's bulkiness in the way. There's just a small number, I think, of ideas like that. Look at that. Stake right away. This is 9, Unit 9. We're going to be looking at radical reactions. And radical reactions are quite a bit different, I would say, than the reactions we've looked at so far. Actually, a few of the reactions we've looked at so far are radical reactions in disguise. Radical reactions are extremely important in biology. They're extremely important in manufacturing. And I'm going to show you how this works, what free radicals are, how we can think about these. And it's, I'd say, a small step from what we already understand about what I would call ionic reactions to go into the other kind, which is radical reactions. So all the reactions we've looked at so far, at least in terms of mechanism, are what I would call ionic reactions. They have ionic either starting materials or intermediates, but I would say what really characterizes them is that electrons always move in pairs. And we have curved arrows, curly arrows, with an arrowhead on them, which represents movement of pairs of electrons. So every mechanism, every step, even acid base, everything's moving in pairs. That's typical of an ionic reaction. So if a bond is breaking in an ionic reaction, like in this case, we're losing a chloride to make a tertiary carbocation. We call that reaction a heterolysis. Heterolysis just means you are breaking a bond, and when you break that bond, one of the 2 atoms that was a part of the original bond gets the electron pair. So in this case, the chloride gets the electron pair because the chloride is more electronegative. So that's an ionic reaction. We've made 2 ions. Electrons moved in pairs. So in a radical reaction, what happens is electron pairs, when they break, they don't necessarily break so that one partner gets both of them. They break so that each side gets one of the 2 electrons in the pair. So here's a reaction. We have a molecule ROOR. These types of molecules are called peroxides. And what's happening with this peroxide is that OO bond breaks, and they both don't go to one side or the other. That pair splits such that one electron goes to one oxygen. You see there's one there. The other electron goes to the other. This is called homolysis. Homo means same, so it means both partners end up with the same number of electrons from that pair. Or hetero means different. The two partners get different numbers of electrons after they split. Great. We use curly arrows as well to represent homolytic bond breaking, but we don't use the regular arrowhead. We use one with like a half arrowhead. So however you've been drawing, people like to actually like draw the arrowhead out. We're going to draw half an arrow. Half an arrow represents one electron moving, and if you have a pair of electrons that are moving, you need to have two of these arrows to correctly show what's taking place here. So here we have homolysis. We use two half arrowhead curly arrows. That bond breaks, and each partner gets one electron. So these free radicals have quite a bit. So these things are called free radicals, by the way. Free radicals are compounds that have unpaired electrons in them somewhere. They react quite differently than nucleophiles or electrophiles because these typically do not react with positive or negative centers because they can't accept a pair of electrons and they can't donate a pair of electrons. They're not really nucleophiles or electrophiles, like basically every other intermediate that we've seen. What they do want is a full octet. That's common among all molecules. They want full octets, so they want to do reactions that'll give them a full octet. But for this oxygen right here, to get a full octet, all it needs is one more electron. So it'll do a reaction that'll steal one electron from something else, not pairs. In terms of geometry, free radicals, at least if they're on carbons, the carbons are sp2, and probably the best description of their shape is trigonal planar. They're actually not perfectly trigonal planar. They're, what do they call it, a shallow trigonal pyramid. So basically there's a bit of an angle to them, but they're closer to sp2 than sp3, so we call them sp2 hybridized. So you can imagine in this example, that's an sp2 carbon, and you have the p orbital above and below. That electron is residing in that p orbital. Now radicals, carbon-centered radicals for sure, are electron poor because they don't have a full octet. Just like carbocations, they are stabilized by alkyl groups because they donate electron density. This isn't as severe as for carbocations. Carbocations are short 2 electrons and they have a positive charge. They're neutral and they're short 1 electron. So yeah, tertiary is best here. But unlike carbocations, you can have primary radicals and you can have methyl radicals. For carbocations, we just said those were off the table. Okay, so yeah, they are electron poor. So what are some reactions that we can do with free radicals? And I said they're important in biology, and that's because free radicals are generated as products of normal metabolism. And so radicals can enter our cells through natural processes, and that can be actually very damaging to our cells, cellular components. And so our body has mechanisms to block the negative effects. There's some dietary reasons as well. Okay, so if you take a halogen, an X2, which in the case of chlorine is a gas, bromine's a liquid, iodine's a solid, these can react with alkanes via a radical mechanism. So an example would be you take methane and you take chlorine gas and you put them together, both gases, and you mix them together. What can happen is you can get this radical reaction that will basically produce a molecule of HCl and a molecule of chloromethane. And this reaction, if you have more chlorine, can happen multiple times. You can make dichloromethane, you can make chloroform, you can make carbon tetrachloride. So you can substitute off all of the CHs if you have enough chlorine gas in there. So this is good. You know, we've got some useful things here. That's a useful solvent. That's a useful solvent. This is actually a decent methylating agent. So using a nucleophile, that'll react with a nucleophile. Carbon tet used to be a useful solvent. So synthetically, this is an important reaction for making things that we want. Chlorine works great. Bromine, a little sluggish, but bromine will go. Iodine doesn't work. Reaction's too slow. Fluorine will just explode. Fluorine is too active. So this reaction is not done with fluorine gas. So the mechanism for this particular one, it's a radical mechanism, and radicals do mechanisms that we call chain reactions. So chain reactions you can think of as being, you know, something that is produced throughout the mechanism starts off another reaction step. So it could be stepwise, they kind of cascade into the next reaction. And you'll see why when I show you the steps that this is the case. As opposed to all the mechanisms we've seen so far. They're all sort of nice closed systems, right? Look at like an SN1. You have your molecule and your nucleophile. Your molecule loses a leaving group, your nucleophile comes in, everything's done. This one, what happens is it starts off, and before the step is finished, it's kicked off another step, and it keeps going. It's like snowballs, right? It keeps going and going and going and going stepwise. And it starts what we call a chain reaction. So the chain keeps going, 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 until something breaks that chain, stops that chain from continuing. Example would be the destruction of ozone in the environment by chlorine radicals. So if you get carbon tetrachloride up in the atmosphere, the sunlight will react with it to create Cl radicals, and that chain on average will run about 10,000 times before it stops. So one atom of chlorine can destroy 10,000 molecules of ozone on average under atmospheric conditions, which is why these reactions can be very damaging, but they can also be very useful as well. Okay, so in this reaction, like all radical reactions, you need what's called an initiation step. You need radicals for this reaction to go. So you need something, if you're not starting with radicals, you need something that can create radicals for you. And in this reaction, we call that initiation. This begins by taking our halogen, our Cl2, and doing homolysis. So you need something that can break that bond. You need to put energy in. You can see there's a symbol missing there. You use either heat or light. And this symbol here, H nu, it's not HV, it's H nu. Nu is the Greek lowercase n. And that's because the energy of a photon is equal to H nu. One or the other, you need some energy source that initiates the reaction. Starts it off, nothing happens. You can kind of think of it a little bit. It's kind of like activation energy. Not exactly, but you need to get this thing going. And what this does is it creates two chlorine radicals. And now we can start our chain reaction. Okay, so yeah, we make these chlorine radicals. Then what the chlorine radicals can do is they can abstract a hydrogen atom. They're going to take a hydrogen nucleus along with one electron off of an alkane, like this CH4. So you see what's happened is this single electron from the chlorine has got together with one of the electrons in the CH bond. The other electron in the CH bond stays on the carbon. So now we have HCl. We say this is a stable molecule. It's closed shell. Closed shell means everything has a full octet. Except for hydrogen, it only has a duet, right? It only has 2 electrons. But we've created another radical in the process. All of these steps, we call these propagation steps. They start with a radical and they end with a different radical. Then what can happen is that methyl radical, that CH3 dot, which if it was a carbocation, we wouldn't be able to have it, but we can if it's a radical. This can react with another molecule of Cl2. Remember, there's lots of Cl2 here, lots of methane. And that bond can break where one electron gets together with the electron from the CH3 to make CH3Cl. And we make a new chlorine radical as a result. Realize that we started this whole thing off with a chlorine radical. We started that at the beginning of this step, and after the end of the sequence, we have a new chlorine radical we're ready to start with. So what this will do is do step 1 again. And then step 1 will make a methyl radical that'll do step 2 again. And step 2 has a radical that'll do step 1 again. And as long as you have a source of methane and Cl2, these 2 steps keep going 1, 2, 1, 2, 1, 2. And it keeps going one after the other, and they kind of never finish. Because, you know, if you look at these steps, it's not like SN1, SN2, E1, E2. It's not like there's a start, there's an end, and the story is complete, you have your products. You can't draw this in a nice closed container. This is why we call these a chain reaction. Once you start it off, it just keeps going and going and going. Step 1, step 2, step 1, step 2, step 1, step 2. Every step produces a molecule of HCl and a molecule of CH3Cl. This will proceed until you've run out of starting materials, ideally. There's actually another way that we can stop these reactions, and it's called termination. So we have an initiation step that takes closed shell molecules and makes them into radicals. You have propagation steps, which start with a radical, end with a radical. Termination takes 2 radicals and combines them to make closed shell molecules again. That's a way you can stop a chain reaction. Remember, though, that these radicals are intermediates. The concentration of radicals at any moment in time in one of these reactions is extremely small. They're not long-lived. The chances of 2 radicals colliding with each other is very small. So here's some examples of terminations. Let's say we have 2 chlorine radicals that find each other. They can go back and make Cl2 again. Or let's say you have a chlorine radical and a methyl radical. They can combine to make CH3Cl. Or you could have 2 methyls. You can make a molecule of ethane. These 3 steps are very rare. I would guess, you know, these propagation steps on average probably go back and forth and back and forth and back and forth thousands of times, hundreds of thousands of times before you get the chance termination that'll stop this mechanism from continuing. So kind of the idea is if you start with a mix of Cl2 and methane and you take a camera with a flash, you put light in there, that is absorbed by the chlorine, it makes chlorine radicals, that initiates the reaction. You could just leave it go then, and the reaction will go through these propagation steps, but eventually the reaction will slow down as these termination steps start to stop chains. And then eventually it'll slow down and stop. You could take another picture, another flash of light, start it up again, and it'll continue. What's often done is we do this chain reaction continuously with light because we don't want it to stop. A good example of a reaction like this is when you, if you go to the dentist to get a filling, and they drill the tooth out, and they put that they put like a kind of a gel kind of material in the tooth, and then they have like a little light. I don't know if you've seen it, and they hold it up to the tooth, and they turn the light on for like 30 seconds. What that light does is it starts initiation steps in that polymer, it's in the tooth, and that initiation step starts chain reactions in the material that polymerize it. They turn it from like a soft, gooey paste into a rock hard, solid polymer. And then eventually it just, I don't know if it terminates so much or it just runs out of starting material. But it takes, I don't know, 30 seconds or a minute for that to happen in your tooth. Then you have like a rock hard filling where there used to be a kind of a soft, gooey gel in there. So now we know the mechanism for this step. So here are some examples for chlorination. In both of these examples, there's only one possible product. We're starting with an alkane where all of the hydrogens are equivalent. If you did a carbon-13 NMR spectrum, you'd only get a single peak for both of these starting compounds. Only one possible monochloro product. These reactions, chlorinating alkanes, are most useful when that's the case, when you can only get one product out. So these might be industrial processes where you'd want to get these products for some particular reason, solvents, whatever. Starting molecules to make drugs. The good thing about this reaction is that alkanes are super common. They're super plentiful. They're crude oil. We can get a whole variety of them by fractionating crude oil. We can get long chain alkanes, short chain alkanes, cyclic alkanes. These things are easy to come by, but they're not very functional, right? They don't have many functional groups, so we can't do very many reactions on them. This is a way to take a non-functional molecule, put a functional group on it, and then allow us to make anything we want out of it. So that's why these reactions are important and valuable. They functionalize an otherwise non-functional molecule. They allow us to turn it into something we can then manipulate and turn into whatever we would like. Great. I see your question, Sam. I think I missed the timing there by about 20 minutes. What's happening where two arrows are coming together? So if you have two radicals, those are turning into a pair. They're coming together, and that becomes a pair. In this case, is a bond. Imagine you have this alkane. Not super complicated alkane. You chlorinate this, there's a whole bunch of different products that you can get. Because that chlorine can kind of go anywhere. And it turns out chlorine isn't that selective. It'll give you a little bit of all of these. By the way, this has a chiral center, and this has a chiral center, and this has a chiral center. So there's 3 more in addition, right? There's a total of 9 products that you could get from this particular reaction. 9 if you count stereoisomers. So like synthetically, this is not really a good reaction because, you know, we like reactions that give you one product. We don't like getting a whole mix of 10 or more, 9 or more different things in here. So synthetically, this is most useful when there's only one alkane product possible, like the cases we've seen before. There's a preference, you know, if you can make more than one product, often there's a preference for one over the other. So, you know, if you start with butane, you make 2-chlorobutane, racemic, mixture of R and S, about 72%, 28% is 1-chloro. You could separate these and have, you know, bottles of both in the end, but what we see is that it prefers to put the chlorine on more substituted carbons. It's a preference for the chlorine to end up on a carbon that's more substituted. The preference isn't like 99 to 1. It's like 3 to 1 maybe, or 4 to 1, this kind of thing, which means you're going to get significant amounts of all possible products. We like reactions that give you like only one thing and high yields of that one thing. Great. We are out of time, so I'll wait until next class to talk about bromination, which is the same but different. Okay. Basically the same mechanism, same reaction, same products, small difference, which makes it a slightly more useful reaction for us. Great, thank you everybody, and we will see each other again Friday.